All right, the next step in the electrophysiology of neurons is the action potential. All right, so there's 3 steps to electrophysiology of neurons. The first was resting potential, the second was a local potential, and I've already forgotten the 3rd step. What could it be? Oh yes, action potential. So action potentials are very dramatic moving changes in the transmemory potential, and it occurs along the axon towards the synaptic knob. Action potentials are sometimes called a nerve impulse, right? I like to talk about it in terms of a domino effect, right? We're going to have this little domino effect where we knock down our first domino and all the rest of them are going to fall down. Action potentials start when the axon hillock reaches threshold. Threshold is that magic number we have to get to, -55, right? It turns out that -55 is the voltage change that's required to open our first and then subsequent voltage-gated sodium channels. Action potentials link excitatory local potentials with synaptic transmission. And action potentials require voltage-gated ion channels. First voltage-gated sodium channels, and then next voltage-gated potassium channels. Oh, I forgot I had my drama. There's my dramatic moving change. So how does the axon hillock reach threshold? Because that's what we have to do in order to get an action potential. Well, this is where those excitatory local potentials come in, right? Excitatory local potentials increase the chance of exciting an action potential because they allow sodium to come into the neuron. If enough sodium comes into the neuron during the excitatory local potential, and if enough sodium diffuses its way over to the axon hillock, where we have our first voltage-gated sodium channels, then if we can get to that -55 millivolts with all that sodium coming in, then we'll open that first voltage-gated sodium channel, and that will be our first domino that we knock down that will cause all the other dominoes to knock down. If we want the first voltage-gated channels to open, the total amount of sodium around the voltage-gated sodium channels must be enough to change the transmemory potential from -70 to -55. That's that threshold. All right, this little animation is going to show you what's happening during excitatory local potentials that may contribute to an action potential. Right now we're at rest, we're at -70 millivolts. The axon hillock is highlighted in yellow. We have a stimulus that comes in, opens sodium channels. Sodium comes in, some of it gets over to the axon hillock and depolarizes to -65. Is that enough to get an action potential? If you said no, you're correct. We need to get to -55 millivolts. But what if a second stimulus came right on top of that first one, allowing more sodium to come in, and then we get to -60 millivolts at the axon hillock? Is that enough to get an action potential? No. But what if we had a third stimulus that allowed more sodium to come in, and then we got to -55 millivolts? That is threshold. That is when we would fire our action potential. So here's another way of looking at that same concept. Here we have the neuron cell membrane. The 2 yellow lines is telling you that we're separating an area. Over here is supposed to be the cell membrane at the dendrites and cell body, and over here is the cell membrane at the axon hillock and the axon. In red we have the sodium. Most of the sodium is outside the neuron. Right? A stimulus will come, open our stimulus-gated channel. Sodium comes in. Right? If enough sodium if enough sodium comes in so that the axon hillock changes from -70 to -55 millivolts, then we will initiate an action potential. Right? The action potential occurs when we open our first, about to point, you can't see me pointing, gotta use this pointer. The action potential occurs when we open our first voltage-gated channel. So here, the plus minus is showing you that this is a voltage-gated channel. Right? -55 is the magical number that will open this gate. If we open that gate, we will initiate our action potential. So what happens after we open the first voltage-gated ion channel? Right? The first voltage-gated ion channel allows ions to come in and change the voltage at the next voltage-gated ion channel. Because it turns out that all along the axon, we have hundreds of voltage-gated channels lined up end on end on end. They're lined up like dominoes standing up end on end, right? And if you open your first voltage-gated channel, you'll open all of your voltage-gated channels, because if you knock down that first domino, all the rest are going to fall down too. So the first voltage-gated channel changes the voltage at the second voltage-gated channel, which will change the voltage at the third voltage-gated channel, so on and so forth. That is the actual potential. That's the moving change in voltage. Right? That is the domino effect. So actual potentials start when the first voltage-gated sodium ion channels open, but then other things happen that are part of the actual potential.